Too wonky. I'm going to go on. But it's a big step from organic molecules to life. I mean, the first big challenge that life had, well, maybe not the first, but one of the big challenges life had, complex life, is to learn how to deal with oxygen. I mean, oxygen is toxic to many microbes. It's such a reactive atom, a reactive molecule, that it wrecks things. It's the wrecking ball inside the china shop, you know. And it took a bunch of random mutations to develop cell walls and then mitochondria to channel where the energy was going to be happening, and, you know, to design a cell so that it could efficiently and properly use oxygen without killing itself. DNA codes for nearly all life. Here's another problem. The problem with DNA is that it requires significant chemical catalysts to form, catalysts which are coded for by DNA. So we have a chicken and egg problem. Probably the solution, though, is not that unreasonable, and that is that maybe life really got started with RNA, which is not the double helix here. You can still code for a lot of proteins and do a lot of good stuff with RNA, and yeah, it may not be your best life, but it could be enough of a stepping stone that then the RNA could evolve and become DNA. RNA life could evolve to become DNA life. And then the RNA life would be outcompeted and be gone, and that's why we don't see it out there anymore. All right. Let's rewrite our Drake equation. So, here is the number of planets that we got out of our original Drake equation. Now, it's been realized by people like Peter Ward that there's really a lot of other things that have to go right. And in fact, a lot of these things we didn't really understand very well back in the 1960s when the Frank Drake equation first came along. So our first naive, optimistic original number, NP0, was 200,000 galactic civilizations out there right now, waiting to talk to us. Important to tell you this. So what limits the ability of a planet to support life? It's climate. Stable climate is all important. Now you might say, well, gee, actually messing around with climate can scramble things up and make for a tougher, better adapted life, can't it? Yeah, as long as it's within limits. But if it's not within proper limits, what you end up doing is causing mass extinctions, and mass extinctions can go so wrong you could sterilize the whole planet. Like almost happened during the Permian extinction when we lost 95% of all species of life on Earth. So we need stable climate is the all-important thing. So you're going to see that theme as I go through these other terms. So one thing that wasn't asked was what fraction of these G and K main sequence stars are not variable stars. So we can't have variable stars. Stars which vary too much, they mess your climate. So we're going to have to knock down our number a little bit. Okay, most G and K main sequence stars are pretty stable, but some are not. Some pulsate too much. You can't have that parent star vary by more than about 5%, or it will cause climate to be too variable to adapt to. Variable on short time scales. I mean, time scales short compared to the generations of the life forms you're worried about. So we knock it down, but not very much. I'm going to knock it from 1 down to 0.8. Okay, so not much, but a little bit. What fraction of these suitable stars are single? We didn't even ask that. You know, half the stars in our galaxy are members of binary star systems. Well, that's not cool. Binary stars are trouble. If it's a close binary, it's going to cause all kinds of gravitational disturbances for anything else that wants to get warm enough, close enough to be good. I know there's the Luke Skywalker thing, you know, a double sun in the center, but actually those Probably you're not going to have a living planet on that because the gravity induced by two big stars like that is going to cause variations in your orbit, and quickly even. So probably that won't work. A super wide binary with a very low mass companion, well, you could probably get away with that, but that's not most binaries. Most binaries are close binaries. So if half the stars in our galaxy are members of binary systems, we're going to have to knock this down by half. We need single stars. Okay, what about the fraction of habitable zone planets with circular orbits? Again, we want stable climate. So you can't have a big elliptical, you can't have a very elliptical orbit, is what I'm trying to say. An extremely elliptical orbit is going to cause large changes in climate on a time scale of just 1 year. That is no good. So from Kepler data, it appears that roughly 70% of planets have orbits that are too elliptical for comfort. Shoot, I didn't put that slide in. I actually have that slide, I didn't put it into the show. Anyway. Well, that's serious. We just cut in third all of our available planets. What fraction now have a large moon which can stabilize the spin axis? So a wandering spin axis makes again for extreme climate. We think that Mars goes in and out of ice ages as its orbital spin axis goes from being straight up and down to being tipped at a 45-degree angle to the sun. We don't have any data on exoplanet moons to judge this, but only the Earth has a large moon among the inner planets. And it likely was the product of a unique collision with just the right impact parameters so that the resulting collision debris doesn't fall back onto the planet and some stays in orbit. It also spins up the Earth so we get a rapid day-night cycle. That's good. It equalizes temperatures better. You don't want to bake in the sun for months at a time and then freeze at night for months at a time. You want to have your day-night cycle be pretty quick. Well, we're the only inner planet that has a quick day-night cycle, except for Mars, and Mars is too cold. So that knocks it down another 0.15. This might be too severe, 0.15. How serious really is it to have to not have a moon and not have a stable spin axis? Is it really going to mess your climate too much? Well, the odds of having a lucky moon like this might indeed be only about 15%. The odds that it would be a planet killer if we didn't is probably not as bad as I'm thinking. So maybe this number you could raise up to 0.5 or something. That's a note to self before I show this again next semester. What about the fraction without Jupiters that are in significantly elliptical orbits? Okay, so Jupiter has got 2.5 times more mass than all of the other planets put together. Jupiters, big planets like that, are not that uncommon. Okay, so Kepler data shows, unfortunately, most exoplanets are in much more elliptical orbits than our planets. So it's not good enough to just have your planet be on a circular orbit. You also can't have any strong gravitational perturbers out there, Jupiters, in my parlance here. You can't have them on big elliptical orbits either, because they're going to mess up the orbits of anybody that can sense them. So there's another 0.3, independent of these others that we have to throw in. Okay, what about water? So we really believe that water is essential for life, but now we actually want a civilization. So we need a lot of water to help stabilize climate and give us rain and, wonderful stuff like that. 70% of our surface is covered with water. That's worked out really well. Now, I don't want to quibble about it. 60% probably would have been fine too. 50% probably would have been not too bad. But you don't want to deviate too much from that. You want a lot, because a lot gives you a very stable climate, and you don't want all water, and you don't want no water. So a planet that's nothing but a desert that just has a few oases of water, probably not going to have life. And a planet that is covered with water might have life, but it's not going to have intelligent life, because it's going to have waterborne life. It's going to have fishes. It might have dolphins. But you know what? And as smart as dolphins are, I can hear the marine biologists out there. Wait a minute, you're putting down our dolphins? No, I'm not going to put down dolphins. Dolphins are wonderful. They're great. But, you know, they don't have any hands. They don't need hands. They're probably never going to develop hands. They've got no way to use and do technology. And that means they've got no way to talk to the stars. So maybe they can talk to themselves very well, but they can't talk to anybody else. When you live in a water environment, that seems a danger. Jupiter's Europa, Ganymede, Callisto are all frozen water worlds, but that's frozen, so that's not good. Titan has vast ocean under its frozen ice surface too. Water is common. Okay, I think I have a whole separate thing on this, so I'm going to go on. So I'm really just focusing on water here. And so too little water is not good for climate. Too much water is not good for having an intelligent technological species. So we need continents, but not too many and not too few. And, you know, when you look at the water on the water moons of Jupiter, and frankly Saturn's as well, those are way deep compared to any continents. Way deep. They are so deep that you're not going to have anything poking up. So we need water on our planet, and the nice 4 or 5 kilometers thickness of water that we have, about 3 miles, something like that, on average, seems just about right. You don't want it to be 30 kilometers, even though 30 kilometers is actually not much compared to 8 or 10,000 kilometers for the diameter of the planet, something like that. So it's very easy to have too much water and flood any land where you might hope to evolve a species. So that's another rare, beautiful thing about the Earth. We've got just the right amount. Most planets are probably going to get it wrong. Probably 4 times out of 5, I'm guessing. Okay, here's another issue not talked about with the original Drake equation, a magnetic field. You want a magnetic field strong enough to deflect the stellar wind that's essential to maintain your atmosphere. Too strong a stellar wind, which are common. Stellar winds are universal. All stars have them. Stellar winds will blow away your atmosphere if you're not careful. That's what happened to Mars. That's our best theory of why Mars's atmosphere is so thin. It doesn't have a strong magnetic field. It may have had a magnetic field when it was young, but it doesn't have one now. And we see evidence directly from the missions we've sent to Mars that its atmosphere is getting blasted away at an alarming rate by the solar wind. Solar wind particles come in at speeds of like 300-400 kilometers a second, way faster than the escape velocity for molecules from these planets. The Earth is the only rocky planet with a significant magnetic field. Now, from that, you might guess that this fraction's got to be much lower than what I've given it. But you see, that's also related to why we have a large moon. A large moon came from the collision that also spun the Earth up to a pretty rapid rotation. So that large moon both stabilized our spin axis and gave us a rapid rotation. The rapid rotation helped climate, and the rapid rotation also helped us generate a magnetic field. At least that's what we think. And that magnetic field then is not independent, okay? So this is an issue we haven't talked about yet, but it's something I've thought about each time I go through and come up with a number here. The effect that I'm thinking about, is it really independent of the other effects that I'm putting in? If it's not independent, if they really go together like we're talking about here, then you have to include that. So Bayesian statistics would tell you you've got to account for that, and that's what I've done here. So, but you need not just a large moon, but also a strong field. They won't necessarily go together all the time. So I do have to knock this number down of the number 1. We got to knock that down. 0.6, that's my best guess. Well, we need something else. There's a problem in not having plate tectonics. Plate tectonics is necessary to recycle key chemical elements for life. Hydrogen, nitrogen, phosphorus, sulfur, carbon. You know, if you just have a planet that forms and it's molten and there's no plate tectonics, there's no motion, there's no nothing, you're going to get a very stratified planet, and all those valuable chemicals that you need to develop life that are heavy, things like iron and manganese and molybdenum and stuff like that are all essential for life, they're going to sink out of reach. They're not going to be part of your ecosystem on the surface. Now, you may get some of that from impacts from asteroids and things. I'll grant you that. But we need plate tectonics for other things as well. Not just recycling these elements, but also it produces mountains and rebuilds continents. Okay, so continents erode away under rain. And so if we want to have life remain for billions of years above sea level, then we need to rebuild our continents, and you do that with plate tectonics. There's another reason why it's essential. All stars, as they go through their evolution, they get more luminous. Our sun is already about 25 to 30% more luminous now than it was when it first formed. That's way too much. 30% is way too much to have a climate that you were initially happy with still be happy with it after a 30% rise in luminosity. So what your planet needs is the ability to basically shed layers, shed sweaters as your star gets more luminous. For Earth, that meant shedding greenhouse gases. So the Earth no doubt had much more in the way of greenhouse gases when it was young. And now it's near the low point in its greenhouse gases. The Earth's atmosphere is a very lucky combination of domination by diatomic molecules, nitrogen 2 and oxygen 2, and argon. There's 99% of the Earth's atmosphere right there. None of those are greenhouse gases. But most molecules are greenhouse gases. The only ones that aren't are diatomic molecules, H2, N2, things like that. Those are not greenhouse gases because the centroid of the electrical distribution does not change as the molecules vibrate, and therefore there's no resonance that can be achieved with incoming infrared radiation. More complicated molecules do. Their center of electric charge does wander around, and so they can resonate with infrared, and so they can absorb and emit infrared, and so they are greenhouse gases. So what you need is a way to shed greenhouse gases from your atmosphere. Well, CO2 is removed with plate tectonics because it dissolves into water, making carbonic acid, which falls on landforms, silicate rocks especially, and it helps the CO2 out of the atmosphere, drain it into the ocean. And in the ocean, once you have life in that ocean, the life can take that CO2 and build calcium carbonate shells, makes corals and mussels and all kinds of wonderful things. It's a skeleton builder. And it's a natural sink for CO2 from the atmosphere. And our planet has been doing that and helping to keep our planet with a constant climate even though the sun keeps heating up. So plate tectonics. Well, plate tectonics comes from rapid rotation. It comes from a steep temperature gradient, we think. And the Earth has those things, and part of why it has those things is that collision early on that generated the Moon and made the Earth the most massive of the inner planets, and thereby makes it slower to cool, and therefore steeper temperature gradient, and therefore thin crust, and therefore still able to have plate tectonics. And so, again, plate tectonics, you might think, oh my god, I mean, the Earth's the only planet that's got plate tectonics, so, oh no, Rick's going to knock that number way down again. No, I'm not going to knock it down very much, because again, it's not an independent effect. Once you've already accounted for with another fraction, the Moon factor and the rapid rotation factor and so forth, well then you can't knock it down too much. Still, you could have all of these things happen and still not have plate tectonics. That's possible. So we got to knock it down some. I'm going to knock it down 0.6. Don't nail me too much on the numbers, because these are guesstimates that I made along the way, and I did make them independently, so I didn't know what number was going to come out at the end. But I thought about each one carefully, and I put in a number, and we're going to see what we get. Okay, well, gee, there's more fractions to deal with. What about fraction with significant free oxygen, but not too much? So we had oxygen at 1% for billions of years, but we had no complex life. Just microbes in the ocean. It took development of a significant oxygen atmosphere to permit high energy metabolisms, which gives animal life its ability to cope and evolve quickly and solve problems and quickly and, be smart, generate interstellar communication capability. Oxygen is a real, it's a wonderful thing, but it's touchy and it's dangerous. And used in just the right amount is wonderful, and if it's not in the right amount, it'll kill you. Even today, if we raise the oxygen level in our atmosphere, you might say, well, that'll just give us an even better metabolism, and we'll race around getting stuff done even better. No, you won't, because when you raise it too much, even the smallest forest fire goes out of control, and you burn the whole planet to the ground. Lightning fires will burn out of control. So 21% oxygen is just right. We like 21%. We don't want 30%. We certainly don't want 35%. We don't want 40 or 50%. We also don't want 1% or 2%, because then we're gasping for air all the time. Even 10%, we're probably not going to be as good as we are now. Almost certainly not as energetic as we are now. So what are the odds that we're going to end up with an oxygen atmosphere that's just right? Well, I don't understand the oxygen determiners well enough to give a really accurate number here. But I do have some feel for what's too much and what's too little. Oxygen is a very common atom. I mean, when stars synthesize elements, hydrogen to helium, helium to carbon, and oxygen. So carbon and oxygen are the two most common elements after hydrogen and helium. So there's plenty of oxygen out there, but you don't want too much. You can't have, I guess, a lot and bind it up in rocks, and that's something that the Earth has done as well, oxides. Okay, well, so here's another factor. Now, I said that we needed to have greenhouse gas come down in order to keep climate balanced, but could it come down too rapidly and freeze your planet? Could it not come down fast enough and your planet still boils away? I mean, what are the odds that we're going to get it perfectly just right? So there's the Gaia hypothesis that sort of factors into this. I'm not convinced by the Gaia hypothesis.